So, shall we start? Hi, everybody. So, very sparse lecture today. So, yeah, we talked about the convolution last time, right? So, we had this final example. I guess this was the somehow wrapping up example, which told us how we can do convolution when we have a general input, right? So here the input is, when you look at the input is 3 by 32 by 32. So how many channels does it have, the input? 3 channels, like an RGB image. And then each channel is a 32 by 32 map, right? And then if you wanted to do convolution, so here we have 4 different convolution filters. So we have 4 different kernels, 4 filters. Each of them is shown by 1 color. And every single filter needs to have how many channels? 3, because your input has 3 channels, right? So every single of them going to get exactly aligned on this other input, and then you're going to slide over it, and then you're going to get the output. So every single of these filters get convolved with the input and gives you 1 output map, right? And then we have 4 channels at the output. This means that how many filters we have? 4 filters, right? Every single filter gives us 1 output map, so we're going to have 4 channel output, and this is how the convolution works, right? And once we did the convolution, then at the very, very end, when we have computed every single entry on this output tensor, then what do? We're going to do activation. First activation, right? First we do activation, so we get activated features because we don't want to keep things linear. We do know linear is not enough. We need to have nonlinearity, and then we do some nonlinear activation at the output, and that is in total the convolutional layer. So one convolutional layer going to get a tensor, does multiple convolution with multiple filters, gives you at the output a tensor, which is activated, right? Passed through some ReLU function or something. Now, we talked also about the pooling. So the idea of pooling was that we wanted to just make it shifting wanted to get some sort of filtering out of the input, right? So we wanted to filter out this potential variation inside the feature map. So if we have one particular feature map like this, if we want to do max pooling, we essentially get, again, a filter size. So again, here is 2 by 2. But this filter has no weight, right? So there's no weight, no parameter to learn here. You essentially just look at the window, and then you take the maximum value, and you keep on sliding over your input till you just fill out your output map. And this is going to be the max pooling operation, which we also indicated at this point here that we need to carry the index of the entries which we have collected. We will see today why we need that, because this is going to help us doing the backpropagation. So like here in this example, so we look at this window, we're going to write down the maximum value between these 4 different values, which is 3.2. And we keep on going one by one. We are doing the pooling with the stride 1 here. And then at the very end, we have 1 map at the output. And then for max pooling, we also have 1 map, which is indicating for every single entry here which index of the filter was collected. Like, for instance, here, the index is 2 for the very last guy in this output map, down right. So you see 2. And the index is 2 because we have collected the second entry inside the window, right? So everybody is catching up? Yeah? OK, great. So if I want to have exactly the same size map at the output as in the input, what should I do? I should do 0 padding, right? I can pad 0 around my input so that I just play with the size of the dimension of the output, right? And that one going to help me to just get the same size map. Now, if I want to scale it up, right? If I want to do the mapping with, the pooling or convolution with a stride, How can I do it? Do I necessarily need to do it from very beginning with the stride? No. What do I do? Yes, I'm going to do resampling. If I want to just scale it up, I do upsampling, then I do my operation. If I want to scale it down, then I do my operation, and then I do downsampling. Same thing is going on here with the pooling. So that was max pooling. We could have mean pooling, where we basically just look at the mean value. We talked about this, and we also talked about this, that mean pooling is essentially convolution with uniform kernel. But again, important, we don't have any parameter here, right? So there's nothing in the pooling to learn. It's just operating, doing something for us. That's it. So that's it regarding the pooling. So we talked about this, and as we said, if we want to just change the size, we can do upsampling, downsampling. If you want to scale it, and if I want to just play around with a few columns or rows, we can simply do zero padding to just fit the dimensions as before. Okay. One point here is that typically when you are doing pooling, it doesn't help you to do upsampling. Because if you do upsampling, it doesn't harm, but essentially if you do upsampling, you just add zeros, right? And then when you add zero, I mean, if you add too many zeros, then you can end up as the output the same thing as you had in the input, right? Just think about max pooling, right? So in the example of max pooling that we had, if I have filtered 2 by 2, and I just do upsampling with factor 2, then I'm going to add 0 after every column, 0 after every row, and then essentially my max pooling is going to recover the original guy, right? Copy it. So this is not going to help you that much. This is why in practice we don't do this upsampling before pooling. We could potentially do it before convolution, because there we are learning something, but with pooling you typically don't do it. But downsampling, we usually do it. So we usually do the downsampling, and there is one key point, and that is that we typically keep downsampling for the pooling layer in practice. So you're going to see some example today, and you're going to get it more clearly. So typically what we do, we just do convolution with the stride 1. So we don't care about resampling in the convolution. So we do it by that, unless we really want to scale up. So if we want to do upsampling, which is not happening in classical tasks, but if you really want to do it, of course you should do it. But rather than that, you typically do the convolution with stride 1, and you do it as much as you want. And then at the very end, when you want to just get rid of some features, you do first pooling, and then you do downsampling. Okay? So you usually put the stride for the pooling step, because pooling itself is somehow giving you some benefits by doing a good filtering of your features. Okay? So you first do the pooling, and then you do downsampling. This is usually more efficient. Now, one question that you might have is that, do I need to do convolution after every, pooling after every single convolution? The answer is no. I mean, in most classical architectures, we don't do that. So we usually do convolution for multiple steps, and then we do one pooling. So there is no necessity that you have exactly pooling after convolution. So they could come together, or they could just come separately. So now, typical scheme that, as I told you, is that we do multiple convolution, then we do one pooling with a stride. One other point is that poolings are not having any weight, so we talked about this. Typically, we just keep it that. So say 90% of the time, we simply use max pooling, okay? Because we just do it to get the features somehow smooth, filtered out. You don't really want to learn anything there. But, I mean, if you think about crazy things, then you might be interested to also learn something inside your pooling layer. That is also possible. Filter size of the two approaches is not needed to be the same exactly. But typically, we use the same filter size. So if you are doing convolution with filter 3 by 3, you typically do the pooling with the same filter. But there is no reason. You can change. Okay? So that's it. And now we do know how we can do the convolution. We do know how we can do the pooling. So these are the key two components inside CNN, which are new as compared to what we had in the fully connected neural networks. And then the last thing that we are going to do, we just do a flattening, and then once we have everything inside a vector, then we pass it through one multi-layer perceptron, right? A fully connected feed-forward neural network, right? So this is the last thing, and this is basically what you know, right? You already have done this before, so there's nothing specific about this last part. So the term is flattening. In PyTorch or in Python in general, this flatten is a kind of method you always apply on tensors. You have a tensor dot flatten, then it's going to flatten for you. The root comes from here, so people think of like tensor. It could be very huge tensor, and then when you flatten it, you simply put everything in form of a vector, right? So just to have a short practice, say I have this convolutional layer, this output of the convolution and pooling. So this is a kind of tensor, and then this tensor can have multiple channels. And what I want to do, I want to feed it into my feed-forward fully connected network. So how can I do it? I need to get these guys, put them in form of a vector, and then feed it to this network. And say that this tensor has n by m maps, and then it has k different channels. So if I have k different channels, every single of them being n by m, how many entries I'm going to end up after doing flattening? K times n times m, right? So you got the idea. So n times m times k are going to be the number of entries that you have inside that vector. And now you have one vector. You're going to feed it into your MLP, and it's going to process the remaining. So basically, what you do by convolution and pooling is to just filter out and extract proper or a good kind of features from your visual input. And once you get into a few number of good features, then you are good to process with a fully connected neural network. So CNN, that convolutional part, is basically doing feature extraction for you. So it's not doing something magical. It's the same thing as before, but based on intuition that we want to have a kind of shift invariance, we know that this convolution is going to be a good idea to extract our features. So now, after flattening, as I said, everything is a fully connected network, and that's it. Any question? No question? Okay. So if you got no question, then let's look at this convolution layer once again and see how we can connect it to what we learned before about general neural networks. So look at this guy here. And if you look at this guy, I have one input, and my input is a map, 3 by 3 map, right? And I'm doing convolution by a 2 by 2 filter, and I'm not doing any zero padding or resampling, okay? So if this is the case, what would be the size of the output map? Can you tell me? So if I start here, this is the first window. I'm going to compute one feature. Then I'm going to go one right? And then it's over, correct? Then I'm going to come down, do the next one, go right, do the next one, and then that's over, right? So what is the size of the output? 2 by 2, right? Okay, so I'm going to call this output Z, and then I'll show it like this. So I have Z1, Z2, Z3, Z4. Okay? This is my output. Now, what I want to do, I want to really look at this convolutional layer as a collection of, or a layer of neurons. How can I do it? I could say that there exists one neuron which is computing Z, or basically I'm doing one linear computation to get Z1, right? Correct? And this Z1 is connected to which inputs? It's going to get connected to these guys, right? X1, X2, X4, X5, right? So if I want to show it or connect it to the input layer, so you see here, I put x1, x2 till x9 as an input layer. So basically, I get my map, and I flatten it here, right? And now, this is the output. I again write it down in a flattened form at the output. So Z1 to Z4 are the different outputs that I have, right? And now, if I want to compute Z1, which inputs do I need? X1, X2, X4, X5. So I'm going to connect X1 to Z1, X2 to Z1, X4 to Z1, X5 to Z1. I do not connect X3 because essentially I do not need X3 to compute Z1, correct? Everybody's clear? Now, if I go for Z2, which guys are going to get connected to Z2? 2, 3, 5, 6. Great. So if I go for Z2, I'm going to connect X2, X3, X5, X6, right? Correct? OK. What about Z3? X4, X5, X7, X8. So X4, X5, X7, X8, they are going to get connected to Z3. And the last guy is going to be connected to the last 4 inputs, correct? Everybody's clear? Right? So these guys, I mean Z1 to Z4, all of them are linear combinations, right, of the inputs. And those linear combinations are multiplied with what weights? The weights on the filter. What does that mean? That means that this red link you see here from X5 to Z4, you see it? So this is exactly the same thing as the red link here, right? Because both of them are W1, correct? The weight for both of them is W1, correct? So it's the same thing as the red link here, right? The red edge here. All of them are the same weight, correct? So every color you see here is the same thing, the same weight, correct? So now if I just wrap up everything together, I can show it like this, right? So I have one input layer. Out of this input layer, I am computing a bunch of linear combinations, and then I am activating them, right? Correct? So what is every single guy here? Every single guy. What is this? Z1 and F, this whole link, this whole diagram here. How can I show it? It's a artificial neuron, right? So it's an artificial neuron. Z1 is a linear combination of my inputs. Not all of them, a bunch of them. But it's a linear combination. Then you compute that linear combination. Then you activate it. This is essentially artificial neuron, right? So basically, I have 4 different artificial neurons. And these 4 different artificial neurons correspond to the 4 different outputs that I have in my output map, right? So Z1 is the output of one artificial neuron. Z2 is the output of one other neuron. Z3 and Z4, every single of them is output of one neuron, right? But there is one key difference between this architecture or this layer with the typical layers we had before. Can you tell me what is that difference? Yeah? It is not, yeah? You also? Exactly. Both of you are correct. I mean, there were 2 points, and you mentioned it. So it's not fully connected, and as your friend said, it's also sharing parameters, right? So this is the key difference between convolutional neuron layer and the fully connected layer. So if I look at this guy here, I would note that, first of all, it is not a fully connected thing, meaning that, for instance, here, X3 is not connected to Z1, right? So there are a bunch of edges between X layer and Z layer which are being missed, right? They are dropped. So it's a kind of partially connected, not fully connected layer. This is the first thing. And the second thing is that they are sharing same weights. So if I change, for example, the weight which is connecting X1 to Z1, then I'm going to automatically change the link or the weight connecting X2 to Z2, X4 to Z3, and X5 to Z4, right? So if you change one of the weights, all of them are going to change because they are all the same weights, right? Correct? So all of them are the first weight on your filter, right? So once you change that weight on your filter, all of these links are going to change, right? So they are sharing weights, and this is not a fully connected layer. So no fully connected, locally connected, or partially connected layer, and the neurons have the shared parameters. And this is why we say that convolutional layer is essentially a feed-forward layer, which is partially connected, some people say locally connected, and shares weights. Okay? So what is the benefit of doing this? What is the benefit? What do I gain when I do partial connection and I share weights in terms of computation? You can do parallel computing, that's correct. You can do it faster, but essentially you have less parameters, right? So one layer, I mean, if you just think about the case when you wanted to have a fully connected layer, and don't think about the bias, we don't have bias. How many weights did you need? 9 inputs, 4 outputs, it's going to be 4 times 9, 36, right? But now you're wrapping up everything with only 4 weights, right? So you got a huge reduction from 36 to 4, meaning that when you are doing optimization, you need to compute a gradient of size 4 instead of 36, right? So it's going to be a huge drop in terms of computation. So this is the main reason that we are doing this. It doesn't mean that we couldn't do that with a fully connected. We could have done this, but that's going to be huge computation. We don't want that, right? Everybody's clear? Questions? Great. So if you got no question, then you can think about your pooling layer the same way. So again, pooling layer is a partially connected neural network. Partially connected feed-forward layer. For instance, say, I mean, this is a dummy example, but it's still valid. So I have 4 or 2 by 2 input. So I can look at this input as y1, y2, y3 till y4. So I have 4 different inputs to this pooling layer. And then I am computing pooling with this weird filter, which is 2 by 1. Okay? Sorry, 1 by 2. 1 by 2. Okay? Now, I'm going to put it first on top, and then I'm going to look at, for instance, if I'm doing max pooling, I'm going to take the maximum value between y1 and y2, right? And then I'm going to bring it down, and I'm going to compute, look at the maximum value between y3 and y4. But it doesn't matter what I'm doing. Here I'm looking only to y1 and y2, so I only need to know these guys, so I can think of my pooling operation, whatever that is. It's maximization, it's averaging, like max pooling, min pooling, or even if it is a complicated operation. At the end of the day, it's going to be a function pi, which is taking this y1 and y2 only, and it doesn't need to look at y3 and y4, right? So that's the case here, and again, I am doing the same thing here, right? So again, I'm going to go for y3 and y4, only they are connected to another neuron with function pi, and these guys are going to compute my pooled features, right? So again, you can look at this whole operation here as a partially connected layer, correct? Everybody's clear? Right? Okay. Well, this is the same thing here again. So pooling layer, like convolution layer, is a partially connected feed-forward layer. That's fine. The key difference with the classical convolutional layer is that there is no parameter here to learn, right? So it's like you just put one fixed layer, which is pruning your features, getting rid of some unnecessary features for you. That's it. Yeah? But there is nothing there to learn. Right? So none of the weights connected here, none of these guys are going to be learned. There is nothing to learn here. Right? If you are doing a classical max pooling, for example. Clear? So this is why many people call them like, this is a convolutional layer, because they think of, again, a neural layer, right? And this neural layer is correct. I mean, it's a neural layer, really, but it's not fully connected, right? Pooling is again a layer, but the neurons are fixed, the weights are fixed. You're not playing with that. So you are reducing the complexity of the problem because you do know you don't need that much complexity to learn what you want to learn. Okay? Okay, great. Questions? No question? Great. So if from now on I tell you what is the output of the first neuron, convolutional neuron, you get what I'm saying, right? So I basically Z1 for me, or basically what I get after activation, for me that one is the output of one neuron, and that is correct. Mathematically that is correct, right? So you don't get confused anymore, right? Okay. Now, one other thing, just a short discussion on the idea of going deep with convolutional neural networks. I mean, the idea is essentially the same thing as general idea for deep neural networks. I mean, why we go deep with neural networks? Because as we go deep, we exponentially get more strong, right? So we get stronger exponentially, so we are happy to go deep. But with convolutional layers, there is some sort of interesting interpretation because it has some visual interpretation for us. Okay? So a short discussion on that. There is some idea that people call it like receptive field, some concept. And what is the receptive field? If you are looking on one particular convolutional layer, whatever you get at the output of it, so it's a map, right? And every single entry inside this map is going to be, for us, one neuron, right? So that neuron is somehow connected to the previous layer, the previous map, the map which was at the input, within a specific region of that, right? And if you keep on backtracking it to the very, very input, then this is going to be a specific part of your input image, right? So people used to call it receptive field. And this is basically coming out of that biological story that I told you, because they think somewhere at the very end of your brain, when these simple cells and complex cells are processing the visual scene, so every cell is having one specific receptive field. Okay? So the idea of receptive field is basically the input region where your particular neuron is looking at. For instance, look at this whole thing here, this particular part. You see this red neuron in the first convolution. So this first completely colored map, this is your input map. So you can think of it as one image. Okay? And then when you are doing convolution with filter 3×3, one particular neuron, for example, this neuron here, this guy is looking into this part of your image, right? So it's going to look at that 3×3 part in your input image, and then it computes some feature out of it, right? But if you go further down, so if you come here in the next layer, so you look at this very right layer, and here you see one other neuron, and that neuron obviously is looking into this yellow area in the previous layer, right? But the previous layer is not your input, right? The previous layer itself is a feature computed from the input, right? So if you again connect every single neuron from the previous layer to the input layer, then you're going to get a much larger region inside your input, right? Correct? And that region where every single pixel inside that is somehow impacting this particular red neuron inside your second layer, this is the receptive field of your red neuron. You got the idea? So now, one point here. First of all, if you are just talking about the first layer, finding out the receptive field is quite simple, right? So every single neuron, you just need to know the filter size, right? And then you're going to see which part the neuron is taking from the input to compute the feature. That is the receptive field. But as you go inside, as you go deeper inside, then you're going to see that this receptive field is not simple anymore, right? So you need to somehow compute it. It's not a super complicated thing, but you need to spend some time, right? So for the first layer, it's quite simple. For deeper layers, you need to do some computation. That's okay, but really we don't need it in practice. But one key point here is that as we keep on going deeper and deeper, what is happening to the receptive field? It's going to get larger and larger, right? Because, I mean, it doesn't matter. You don't need to change your filter size. I mean, if you have fixed filter size, but you just keep on going deeper and deeper, as you go deeper, every layer is just expanding its receptive field, right? Everybody's clear? Question? So this is one key or one important idea here, which is telling us that if we are going deep inside a convolutional neural network, the thing that is happening is that every layer is somehow expanding the region where it's looking at the input, right? So your very first layer is just scanning your input very precisely. The second layer is scanning the features precisely, which means that it is somehow scanning the input less precisely, right? So the third layer is scanning the second layer feature precisely, right? So it means that it's just scanning the input much less precisely, right? And you keep on going, you increase the receptive field, so you get a broader perspective from the input, and you can do it properly because you are accessing to that input through the features properly computed by the previous layers, right? Now, few points here. One of them is that if I have large filter, if I increase the filter size, my receptive field is also going to increase, right? So if I have 2x2 filter and 2x2 filter in the second layer, then the second layer receptive field is going to be much larger than 2x2, right? Now, this is one of the key reasons that we are not very happy to have very large filters at the beginning. Because when you have at the beginning very large filter, it's going to somehow reflect to the receptive field of all following layers, right? Because like if in your very first layer you are looking at a very large chunk of inputs, then in the next layers, the receptive field of those layers are going to just get huge and huge very fast, right? So large filters is going to increase the receptive field per every layer, and if you choose small filters, you're going to have a smaller receptive field in every layer, right? And this is a good thing. You don't want to just increase your receptive field very, very fast. I mean, anyways, as you go deep, it's going to increase in size. But you don't want to do it very fast, because this means that if you do it very fast, then in a couple of layers, your layer is somehow it loses the track of input features, right? And you don't want this. You want to keep the accuracy of the layers high enough, right? So now, let me just give you, as I said, this receptive field idea is basically helping you to have a bit of intuitive idea. Let me just give you one simple example. Just look at this nice image of this cute cat. And this cat, I want to pass this through one convolutional layer, okay? And I assume that my filters are 2x2. Now, what's going to happen if I do only two convolutional layers? So this part, which is supposed to be orange, this part, is the map that I'm computing out of my first convolutional layer, okay? And then this green one, which is very light now, so this green part, the green map, this is the map that I'm getting out of my second convolutional layer. So if I'm doing 2x2 filters here, now what is going to happen to this image? I mean, I am going to get, this image has, of course, bunch of pixels, right? So my filter is going to just collect 4x4 windows, right, on this input, and it just goes through those 4x4 windows, and every of those 4x4 windows is going to compute one of the features, right? Which means that, for instance, my very first feature inside the first layer is going to be somehow connected to these inputs, right? So the first feature is only looking at that tiny portion on the top left corner of my image, right? What's going to happen if I go for the second layer? In the second layer, my first feature is going to look at the top left corner of my feature map in the first layer. And that guy is going to be much higher at the input, right? Now, here is 2x2. I mean, at this point, in the first layer, this guy is 2x2, right? Correct? The receptive field is 2x2. When I go for the second layer, it's going to be, what is it at the input, the receptive field? 4 by 4. If I go for the third layer, what do you think? What it would be? 8 by 8, right? So again, it's the same thing as we had before. As you go deep, exponentially you're expanding your receptive field. So very careful, we should be very careful when we are choosing the filter size, because it's not only like I have a very large filter, I have so many parameters. You are just increasing your receptive field, right? And this is increasing very, very fast. So exponentially, essentially, right? Okay? So moral of the story here is that as you go deep in convolutional neural networks, you are going to gradually increase your receptive field. And this gradual increase of receptive field help you to get gradually a kind of big perspective on your input, right? So this is the first point. In the first layer, you're just somehow scanning the very small portion of your input. But then in the next layers, you're increasing that portion. But you don't do it directly on the input. You just do it on the previous layer, right? But this is somehow going to backtrack to your input in that way. And we could somehow argue that the first layer are somehow extracting the low-level features of your input. So it's looking at the top, the corners, what is happening in the corners, what is somehow some sort of, what kind of property you see in a tiny receptive field inside your input. And then the deeper layer is somehow looking at the high-level features, right? So it's going to say like, okay, the combination of this part and this part is an eye, right? And this eye has these kind of features, right? So it's going to extract those guys. And as you keep on going deep, at some point you're going to collect lots of high-level features. Then you give it inside to your MLP. And your MLP is going to see, okay, these are the features of the eye. Now let me classify this animal. This is the eye of a cat, right? So it's going to find it out based on the features gradually extracted by those convolutional layers from your input. Okay? So that is one cool point, or one cool operation being done by the convolutional layers. And the key point here to have a kind of very refined form of feature extraction is that we should be careful with the size of the filters. So a general rule of thumb, when you are in your first layers, you should keep your filter size small. Even if you want to increase your filter size, keep it for later, okay? Because in the first layers, if you just do very high filter size, then as you saw, this is going to somehow propagate over a whole deep network that you have. And at some point, your convolutional layers are going to lose the track of the input features, okay? So typical thing that we just choose small filters at the input. And then because of that, we're going to have large filter maps because you have small filters, and then you don't really reduce so much in the maps in the output size. And when you go deeper inside convolutional neural network, it's okay if you want to have larger filter. Practical thing, we always keep the filter size fixed and small. I mean, even those crazy architectures that you know, they always have 5 by 5, 7 by 7, sometimes even 3 by 3 filters. And this is the whole magic of this convolutional layer, because with just a few parameters, it can do the job for you. Because the problem is not complex, like what we started with, that finding out the MNIST image or classifying the MNIST image in a very big background, it's not a hard problem, right? You only need to somehow find out where the image is, and then that's it. That's over, right? So you don't really need a huge layer in practice. If you want to have so many parameters, just keep it deeper and deeper, okay? So just keep small filters, but just do it over and over. Do it enough so that you extract enough features. Okay. Any questions? Yeah.
For the last page, would you refer to the output channel?
Sorry?
For the last page.
Yeah.
What do you mean by output channel?
Where, in which part?
Channel.
Output. Okay, I don't see where. I mean, output channel, I simply mean the channel, the map that you compute at the output. I don't see which line. Oh, last line. The number of output channels, right? The output of your convolutional layer is a tensor, right?
Yes.
In general, right? And then it has multiple channels, right?
But the number of channels really depends on
On the filters, right, right. I'm going to show it, I'm going to explain it in the next slide. But yeah, good point. So one thing that I wanted to indicate here, I just kept it for the next slide. But since you asked, so typically what you do, you're going to have like few channels at the beginning, and you are going to increase your channels. But I'm going to show it in the VGG architecture. That's going to be easier for you. Because you want to somehow prune your features and just somehow break them down into more channels. And then every single channel is looking into one particular high-level property. But I mean, I don't think that immediately you see it here. Maybe I show it on the VGG architecture and you see it more clearly. Questions? No question? Great. So if you got no question, then let's just look at this VGG16 architecture. This is the one which I showed you when I just concluded that in convolutional neural networks, we are going to do convolution, pooling, and feed-forward neural network, right? And at that point of time, probably you couldn't find out what are these numbers here, but now you can easily do that. So let's just look at this. So first of all, in this architecture, we're going to talk about this in the next chapter. So this is one of the breakthroughs in convolutional neural networks. And this guy has every single convolutional layer that you have. It has multiple filters, and every single filter inside that is 3 by 3. So you see how small that is, right? So you have just 3 by 3 filters. Okay? So they do padding always, zero padding, so that they keep the input and output size the same when they are doing the convolution. And then they always, once they did multiple convolutions, then they are going to do max pooling. And for max pooling, they do it with a stride 2. And the reason for that is to just make the size of the input half. Okay, so they want to reduce the size of the maps. Okay, now how does it happen? Let me just show you this one. And unfortunately, I could not make it larger than that. I don't know if here oh yeah, I can. You see it here, right? It's better now, right? So this is your input. This is your input image, right? You see this guy, and this is image of the data set ImageNet. So do you know what is ImageNet? So ImageNet is a data set which has a huge number of images, and it has 1,000 classes. 1,000 classes: cat, dog, airplane, car, frog, and so on. I think Bruce did some experiment for you on Tuesday with this data set. Okay, so you have 1,000 different classes, and you want to look at the input image, and the input image, looking at this input image, you want to classify that image, whether it is, which of those 1,000 classes that is. Now, looking at this number, what is the size of your input? Can you tell me? Here. 224 by 224 by 3. What does that 3 mean to you? 3 channels. So obviously, right? It's an RGB image, right? So 3 channels, R, G, and B. And what is the size of every single map in this RGB image? 224 by 224. So it's 224 by 224 pixel image, RGB, right? 3 channels, 224 by 224. And then you do convolution, one convolution. 3 by 3 is the filter size. Okay? Don't get confused by this 2D. This 2D here is or 3D yet. Okay? So it doesn't mean that they are really having 2D. I mean, since they are doing it in 2D form, some people call it 2D. So don't get confused with this 2D. Forget about this. And now you have 3 by 3 filter. So if you have a 3 by 3 filter and you are applying it on an input with 3 channels, how many channels do you have in your filter? 3 again, right? So what is the actual size of one filter in this architecture? That is 3 by 3 by 3, right? This is the size of one filter that you have. So this is one two-dimensional filter that you have, 3 by 3, but you don't have only one of them. You have 3 of them, right? Correct? Everybody's clear? So how many weights do you have in this filter, in this guy? 27 different filters, right? Weights, because this has 9, this has 9, this has 9, 27 weights in total. Now, after you do the convolution here, this is the dimension of the output, 224 by 64, okay? So, first of all, every single map is still 224 by 224. Did I do zero padding? Yes or no? Yes, I did zero padding. Great. So what is the stride? Stride is 1, obviously. The size has not changed, right? So stride is 1. The stride is 1. I have done zero padding. That's fine. And now I have one output tensor with 64 different channels. How many filters did I have in this layer? 64 filters. So this is one filter, and I had this till number 64, right? So this is W1, and I had it till W64. Everybody's clear? Right? Does it make sense? Yeah? So now if you want to see how many weights you have, basically here you have 27, the next one 27 till the last one. So you have 64 times 27 different weights in total in this layer, which is large, but it still is much, much, much smaller than what you should have done if you wanted to go fully connected. Right? Everybody's clear? Now, you got from this layer, look at this layer, to the next convolutional layer. And again, it's written here 3 by 3. It means that the filter size is 3 by 3, right? So the filters are 3 by 3. Then this is the output of your second convolutional layer, 224 by 224 by 64. First of all, what is the size of every single filter in this what is the number of channels in every single filter of this second convolutional layer? 64, because the input to this convolutional layer is a tensor of depth 64, right? So every single filter that you have is now 3 by 3, but here it's 64, right? So it's going to have 64 times 9 different weights, right? Correct? Now, what is the number of channels at the output of this convolutional layer? 64 again, right? So how many filters did you have? 64. Great. So you're seeing this. So now you get 224 by 224, 64 different channels. Now you do a max pooling, okay? And now when you do max pooling, you're going to keep the channels the same. The reason is that you are doing the pooling on every single map, right? So you have 64 different maps, 64 channels that you have. You do max pooling on every single map, then you're going to get the corresponding map at the output, right? So the input is 64, the output is again 64 channels. That's clear, right? Now, when you look at this number, is here 112 by 112. Comparing with the input, what is the stride of this pooling? 2, right? So the pooling is done by stride 2. It means that you can think of a normal pooling and then you do downsampling, right? So the only purpose of doing this is to get into smaller maps. And now after you did this, then you go for the next convolutional layer. You see it here, right? And then you see the output of this convolutional layer is 112, 112. Every single map is 112 by 112. And how many channels do I have? 128, right? So how many filters did I have here? 128 different filters I had in this layer, right? 128 filters. Every single of them is just getting convolved with 112 by 112 by 64 tensor at the previous layer. Everybody's clear? Yeah? So now what is happening here? I got this 224 by 224 image, right? And I did some convolution on it. And then at some point, I was confident, like I have extracted enough features, right? Now, what can I do? The next thing that I'm going to do, I'm going to get rid of some features which I think they are not very important, right? So I just do pooling. Pooling is going to do that for me. And I go down, right? Now that I have gone down, so I have same number of maps, right? But these maps are now smaller, right? Now, my final purpose is that as I go deep, I get smaller and smaller maps. But I don't want to lose information. So if I want to make the maps smaller, what should I do? I should increase the number of channels, right? So now in these layers, in the next layers, I am just doing more output channels, right? So if I want to think about it intuitively, it means that I am just first looking at the image of this cat, and I am somehow inspecting it very accurately. But after writing down a few things and pruning them by pulling, then at some point I'm going to say, okay, let me resort every information I collected. Okay, there is some part of this image containing eye. And this eye has this kind of properties. Like the eye is very edgy at the sides, is very round at the top, right? Some part of this image has snout and face and things like this. So let me also summarize the kind of properties I have seen in that part, the snout part of the image, right? And I write it down in every single channel, right? And as I keep go further and further, I am going to get lots of channels, and every channel is just looking at one high level feature of this image. For instance, well, you know, this image in general looks like an animal, right? So what is the chance of this being animal? Or what is the sort of properties that it correlates this image into an animal? I'm going to write it down in the first channel, right? And then the second one is that how many eyes, how many eyes are feasible in this or visible in this image, and how they are in general. So I'm going to write it down in another channel, and I keep on going like this. Okay, it's like you are trying to understand something, so you stand by the coast and you try to understand what is happening. So for the first couple of hours, you're just looking at the waves of the water coming to you and the things inside the water just going up and down. And gradually you start to write some bunch of features, right? I saw this observation, and so on. Now that you want to describe whatever you have seen, you're going to just collect those observations, put them in different classes, right? So during the morning, I had this observation. During afternoon, I had this. And then again, you're going to prune those stuff, right? And then if you want to describe this scene in general, you don't really need to explain every single details happening through the hours you were watching. You just need to give a very brief summary of what you have seen in different respects, right? So every single of those channels at the very, very output is giving you that brief summary. And this is why they are very small in size, every single map, but they are a lot. Okay? And as you can see, you are doing it again and again. So you keep on doing the convolution here, and then you do one pooling again. Now you have 128 channels, but they are much smaller. So 56 by 56. And then again in the next layer, look at it here. You are computing more channels, 256. So you increase the number of channels by factor 2, and every single of them is small, right? And you keep on going like this till you end up here, right? So here is the last layer that you do, so 512. And this 512 different channels having 14 by 14 different feature maps, right? So very tiny feature maps, but a lot of them. And somehow every single of them is describing this whole image at the input completely with few parameters from one specific perspective, right? So it's like you have the image of the cat here, and then you want to find out whether it's cat or not. So you get the first guy, you put it here. This is looking at this image from one specific perspective, and it says, the eyes in the snow tells me it's a cat, right? And the second guy is standing here, and it says like, oh no, the ears tell me it's a dog, right? And then the guy number 512 is looking from here, and he says, no, it's a cat, right? I see it from the fur or whatever, right? And then you just collect all of these 512 different people perspective, and then you give it into your MLP to find out whether it's a cat or dog. So that's it. So you're going to get this 14 by 14 maps, and finally you even do one other pooling on that, so you're going to end up by 7 by 7, so it's not only 49 different values in every single map, but you have 512 of them. And now you flatten them. So this number, 2000, what is it? It's, oh my God. So it's 25,088, right? No, that's right. 25,088 is this, just multiplying 49 by 512, it's going to be this number, okay? So you got this all 512 feature maps, and then you just put them in form of a vector, and now you process them by a dense network. Dense here, it means fully connected. Yeah? And the fully connected layer, this is your first layer, this is your next layer, the next layer, and your very last fully connected layer has 1,000 outputs. Why it has 1,000 outputs? For 1,000 classes that you have. So if you want to classify, what should you do later with this 1,000? What? Softmax, great. So you're going to pass it through a softmax, and that output of softmax is going to give you a bunch of probabilities, and then the one which has the highest probability you're going to choose as the class, right? So everybody's clear? Everybody's happy with CNN? Does it sound nice?
When you jump from, for example, 64 channel to 128 channel, you can control, is it 64 to 128 or directly from 64 to 526, right? You can control that.
You can control that, of course. I mean, if you want to jump very fast, you can do it, but I mean, you can guess, based on what we have learned in this course up to this point, is that if you do everything gradually and slowly, it's going to be better, right? Because you somehow do not miss anything in between. But of course you can do it, right? Yeah.
At the start of the class, you mentioned some image competition that neural networks, like deep neural networks.
Yeah, ImageNet.
That's this? Or?
No, this is not the competition. The data set is the one used in the competition, right? We're going to talk about it in the next chapter, no worries. Yeah. But it's the same. I mean, this guy, this VGG won the competition in 2014, right?
This is the thing that did better than it was a spike after Google did something, and this is the thing that beat that?
No, this was not that. So the one which just spiked deep learning, that was AlexNet. So that was much simpler than this one. So this was later, when deep learning got to be a thing. Yeah, but we're going to talk about it, no worries. So now, any other question? No question? Okay. So now, if you want to count the number of layers, you usually do not take into account the pooling layer, because essentially the pooling layer has nothing to learn, right? There's no weight there. So you have first convolutional layers, second 2 convolutional layers, third 3 convolutional layers, and so on. So if you add all of them up, plus the fully connected layers that you have, the 3 last fully connected layers, it's going to be 16 layers. And the reason we call it VGG16 is simply because it has 16 different layers. Okay? But as I said, we're going to talk about VGG in particular and ResNet in the next chapter. So, any questions? So so we're going to have a break, and our colleague is coming from the well-being project. So they are helping us here at UofT to shape better condition in our classrooms. I think he wanted to just give you a short description and a survey. Okay, shall we go on? Oh. Sorry. So it just... Okay, so training them. So the next thing, I mean, we do know how convolutional neural network work. And I mean, obviously, you can do forward pass right now, right? So if I give you an image and then you want to just pass it through a convolutional neural network, you essentially can do it right now, right? You do know every single operation when it goes forward, right? But if you want to do training, what you need to do, you need to do backward pass as well, right? So we need to backpropagate to compute the gradient. So this is the next thing that we are going to do. So basically, we have a bunch of learnable parameters in a convolutional neural network. And what could be those kind of learnable parameters? So we could have weights and biases, right? And these weights and biases are happening in our filters, right? Convolutional filters. So we could have those guys. And we could have a bunch of weights and biases inside or, very end feed-forward neural network, the fully connected part, the MLP side. And also, if it happens, this is not really happening in practice, but if it happens that we have some weird kind of pooling which has weights again, then they are also parameters that we can learn, right? And then what we're going to do at the very end of the day, so we have a bunch of weights. We can just collect all of them inside one list, and we call it W, right? So W is everything, all of those filters that we have in the convolutional layers now, all of the weights we have inside our MLP, and they are all collected into one list, and then we can compute what we called it before, the empirical risk, right? So now, in this case, how does our data set look like? What is the input? What is the data sample that we have? It's, for instance, an image, right? And that image could be an RGB image, right? This is one sample, right? So you're going to get one sample, which is image of a cat, and then it's labeled as a cat, right? So your data set is going to look like this. So this X is what kind of object is it? It's a tensor, right? So you have one tensor, and it has one corresponding label. That label is V, right? For instance, it says it's a cat image, right? So you have a data set of this form, and you have a lot of them, maybe 1 million of them, right? So lots of images. Every single of them is having one label, correct? So this is the case. And then now that you have this guy, so I can get this image, and I can pass it forward my convolutional network, right? So I can put this RGB image as the input, and I can keep on computing the output till I get to the very, very end. And like what we did in the VGG architecture, at the very end, I can find out the probability of every single class, right? And now, if I want to find out the loss, what should I do? I compute the cross entropy between that probability and the true label, right? The true label of cat. So I'm going to compute some loss. So let me show the output of my convolutional. Oh, I think when I increase the size, yeah, now it's no. Oh, I played with the. Okay, now it's fine, right? Yeah, no, it's fine. Okay, so now. Let's say the output of our convolutional layer is theta. So theta is essentially the output of that softmax that you told me in the previous slide, right? And now that you have this guy, you essentially can feed it into one loss function, for instance, the cross entropy, and you can compute the loss, right? So this is the loss for one single sample, right? And you need to keep on doing with all of your images, right? So you keep on sending all of your images. I mean, right now you do know that this B is not the whole data set size anymore, right? B is essentially your mini batch size, right? But at the end of the day, you are going to send a bunch of those images, and you compute the output, you compute this empirical risk, and then you try to minimize it against the weights, right? And the way, how do we do this minimization? How we solve this minimization problem? Gradient descent, great. So we need to compute the gradient with respect to all of those weights. So we're going to solve this with one gradient-based method. It could be gradient descent itself, the stochastic gradient descent, the basic one. It could be atom optimizer. It could be, I don't know, RMS prop. Whatever it is, at the very end of the day, you need the gradient, right? So you need to have the gradient, and then you can do any of those algorithms, right? So you're going to need this one, and if you want to compute the gradient, obviously you need to do the chain rule. So forward pass, backward pass, right? So that is the whole idea of training one convolutional network. And of course, if we want to do it efficiently, we need to go on the computation graph, right? So we're going to get our data points. So x, I mean, again, we don't need to really think about, I mean, we are not doing batch normalization here. So forget about that. That's going to complicate everything. So we're going to think about the standard version. And if you want to do in the standard form, you just simply need to consider one single sample, right? So in that one single sample, that x is fed into my neural network. And then I'm going to do one convolution. And this convolution is with a bunch of weights, say weights W1. I mean, maybe it's lots of weights inside that. So I'm going to collect all of them in one list. And then I'm going to compute the first output Z1. This is the output of the convolution. This is the linear output, right? And then I am going to do some activation on that, right? So I'm going to activate it. And then I'm going to compute the first activated output. I might do some pooling on that, right? I could do some max pooling on it. And then I get the output of that max pooling layer, right? And I keep on going forward, right? So I keep on doing it over and over and over. At some point of time, say here, you see this y hat L? At this point of time, I am over with all of the convolutions. So when I'm over, what I'm going to do? To the fully connected, right? And if I want to do that, first of all, I do flattening, right? So I'm going to get that weird shape tensor. I put it in a vector, right? So this is why I'm showing it with a vector form, y hat. This is a small letter now, right? So that y hat is now the flattened version. And then this flattened version is going to pass through my fully connected network, right? To give me the very output theta. This is the output of max, softmax, for instance. And out of this guy, and given the true label, I can compute the loss, right? And now the question here is that I want to just be able to compute the gradient of this loss, this sample loss, with respect to any weight inside this computation graph, like W1 here, or anything in between that is there, right? Now, we need to do it by going forward and backward on this network, you can guess. And let's go and see how it's going to look like. So forward pass is quite obvious, right? Forward pass is basically what we did in this lecture and the previous one, right? So I'm going to get x. I pass it through a convolution. This is a convolution computation. I get Z1. Z1 is activated, gives me Y1. Y1 is max pooled. I'm going to get Y1 hat. And I keep on doing it over and over till I'm over. And then finally, I flatten. I do the forward pass on the fully connected network. You do know that as well. So it's basically matrix vector products. And then you're going to get at the very, very output what you want, right? So forward pass is easy for you, right? So that's obvious. Now, once we are over, one important thing. Once we are over, just remember, when we do the chain rule, when we do the backpropagation, if you want to compute the gradients, we need to know the value of every single node, right? So this means that when you are doing convolution, you need to know all of the outputs of the convolution, right? You need to know the value of the activated versions, right? So again, exactly like before, you need to do your forward pass completely. You need to know the value of every single node on the computation graph. Once you know it, now you're able to do the backward pass, right? Now we want to do the backward pass, okay? And trust me, this time is going to be much easier than before, okay? It's going to be, because you got used to it, and it's going to be more intuitive this time, okay? Now, when we want to do the backward pass, we first start by getting from the loss to this guy, right? Can I get to this one? Can I compute the gradient of the loss with respect to the output? Yeah, obviously. I mean, I do know the loss function. It's cross entropy. I can compute that, right? Now, if I want to get from theta to the very input of my feed-forward neural network, the fully connected network, can I do that? Yes, you do know it, right? We just went through it in chapter 2, right? So we do know how to move backward over every single of those fully connected layers, right? So we don't need to redo this. I mean, we really know how to get here. So backpropagating over this FNN is basically what we have done before. So we're going to get into this guy. And once I got into this guy, now I am at the output of the very last convolutional layer, right? Everybody's clear? Yeah? Now, what I do, I mean, this y hat L, I told you this y hat L is the flattened version, right? Is this version, right? But I do know how I have done the flattening, right? So it means that there was one y hat L, which was a tensor, right? So it was something like this, right? It could be multiple layers, multiple channels even, right? It was something like this, and I had a bunch of values here, say for instance A, B, C, D, and then I had, I don't know, E, F, and so on, and then I put them here A, B, C, till N, right? A, B, C, D, and you go down, right? This is the way that you do flattening, right? So you're going to get, okay, first channel, first entry, up, the second one, down, next one, down, and so on. I'm over with this one. Now I'm going to put E, and I keep on going, right? This is how you do the flattening. So you really know the order that you have put things here, right? Now, when you go backward, you are going to compute the gradient of R hat with respect to this Y hat L, with respect to this weight. How does it look like? What is the dimension of this guy? Say this vector here is of size D. What is the dimension of this one? D again, right? So every single entry inside that gradient is the partial derivative with respect to one of those entries, right? So I can, now what I'm going to see here now, instead of y hat L, when I'm doing backward, I'm essentially getting the partial derivative of R hat with respect to A, right? Partial derivative of R hat with respect to B, and so on, right? Now, what I can do, I can simply put everything back inside a tensor form, right? That's going to make my life easier. So I'm going to get this partial derivative of R hat with respect to A, and I put it exactly the place that A used to be on the tensor, right? So I'm going to put here the partial derivative of R hat with respect to A. Now here, partial derivative of R hat with respect to B, and so on. Okay? So I'm going to put them back onto this one. And instead of showing it with the gradient with respect to a vector, I am now going to say that this is gradient of R hat with respect to tensor YL. Okay? Everybody's clear what I'm doing here? So it's essentially just resorting everything back. Right? So everything got on its position on the tensor, right? So once you have this gradient with respect to y hat L, the flattened vector, you can essentially put it back in the form of a tensor. So you are not doing anything. There is no backpropagation involved here. You basically just resort things, right? Things were all vertical. Now you put them back into a three-dimensional shape, right? And you do it exactly the way that you did it when you were going forward. Okay? Everybody's cool? So now we are here. We do have this gradient, and we really don't need to do anything further than what we did before. So simple backpropagation going to get us into this guy. And now the question is that how we can get backward through the pooling layer and through the convolutional layers. Okay? Everybody's clear? So once I do know how I can move backward on pooling, how I can move backward on convolution, and how can I can move on resampling layers, which are not real layers, but we can do resampling. If I know how I can move backwards on those operations, then it's over, right? So I can just move backward towards very beginning, And then I can figure out how I can compute the gradients with respect to weights from the gradients that I have in this computation graph. Everybody's cool? Yeah? So you got what is the problem now, right? So the problem is that I have this gradient with respect to y hat L, which is the last convolutional layer or pooling layer output, the very last layer before I flatten, right? So I have that gradient by backpropagation up to this point, and now I want to know how I can start computing the previous gradients. Okay? So let's look at it. Let's first start with pooling, and you're going to see that this time it's going to get even easier. So let's look at pooling, and this is a pooling, and I have an input. It is 3 by 3 input. Okay? So this input is usually the output of the previous convolutional layer, right? So the convolutional layer did the convolution, did the activation, I got some y map. And now from this y map, I did a pooling and I get the y hat map, right? This is the pooling layer. Now, to keep life easy for us, I always think of feature maps. I don't think of layers yet, channels yet. And then we're going to see that that's super easy once we understand this. That is like super easy to map it to the high dimensional tensor. Okay? But right now think about maps only, and also right now think that I don't do any sort of zero padding. Okay? Because that is doing essentially nothing. Okay? So now if I want to do the pooling, what I do if I do max pooling, say for instance I do max pooling here, and then I see that y2 is the maximum value. What do I put here as the first feature? y2, right? Next one I do, again I see y2 is the maximum between these four, so I'm going to put it as the next pooled feature, right? Now I come here and I see that y7 is the largest guy, so I'm going to put it at the output. And then finally I come here, I see y9 is the largest guy, so I'm going to put it there. Okay? Everybody's clear? So I did pooling, I got into this one. Now what is the problem that I have? I do know what is the gradient with respect to y hat, right? So I got from this guy to this guy, right? I do know what is the gradient with respect to y hat. I do know this map, this index map here. This is the one which I told you we need to keep it, right? So for instance here, what is the index? Index of the one which is maximum is 2, because here is 1, 2, 3, 4. Here is 2, right? Now, here the index is 1. Everybody sees why it is 1? Because on this red window here, y2 is located at index 1, right? So I'm going to put the index 1, right? So when I am doing the forward propagation, I keep this index map, okay? Now, I have this index map. I have that gradient with respect to the green tensor, or green map. I want to get the gradient with respect to the blue map. How can I do it? Everybody's cool? Yeah? Okay, so let's do it together. First of all, let me just compute the gradient. Look at it here on the board. I want to compute the partial derivative of r. First of all, when I say the gradient with respect to y, the blue one, what do I mean? I mean that I need to compute the partial derivative with respect to y1, y2, y3 till y9, right? And I put it exactly on the same map, same size map, right? Everybody's clear? Now, the first thing that I need to compute is the partial derivative of r hat with respect to y1. Okay. Now, how can I write it down if I want to do chain rule? I have partial derivative of r hat with respect to y hat 1. I have it. What should I do next? Derivative of, tell me, what should I multiply here? With respect to? Great. Should I stop? No. I have y hat 1, y hat 2, y hat 3, y hat 4, right? Now, of course, you are not seeing that they are all the function of y1 here, but they could be, right? not in this max pooling example, but in general, right? The whole y hat is computed from y, right? So I can keep writing that down. If they are not a function, then the derivative is simply 0. It's going to disappear, right? Right or wrong? Everybody's clear? So if I go on, so I'm going to write derivative of r hat with respect to y hat 2 times derivative of with respect to? Great. And I keep on going till I'm over with all y hats, right? Everybody's clear? Questions? Okay, so if you got the ideas, now look at this guy. What is y, what is those derivative? I mean, you have 4 of them. What is the derivative of y hat 1 with respect to y1? Is y hat 1 a function of y1? Y hat 1 here is y2. So what is the derivative of y hat 1 with respect to y1? 0, right? What is the derivative of y hat 2 with respect to y1? What is the derivative of y hat 3 with respect to y1? Y hat 3 is y7. What is its derivative with respect to y1? What is the derivative of y hat 4 with respect to y1? What do you conclude? What is the derivative of r hat with respect to y1? It's going to be 0, right? So you're going to write down the chain rule. You're going to say, okay, derivative of r hat with respect to y1. If I want to compute it, I just use the derivative of r hat with respect to every single y hat I that I have. And then I multiply it with the derivative of y hat I with respect to y1, right? And I sum it up. Here in this example, it's going to be 0, right? Now, let's do it once again for y2. So if I want to compute the gradient or partial derivative of r hat with respect to y2, then what should I do? Should I touch the first term, r hat with respect to y hat 1? It's going to stay here. Y hat 1 with respect to y2, great. So it's going to be y2. Again, r hat with respect to y hat 2, y hat 2 with respect to y2, and you keep on going, right? So let me get back on this diagram here. So what is the derivative of y hat 1 with respect to y2? 1. What is the derivative of y hat 2 with respect to y2? What about the other guys? So everybody who has y2 is going to have gradient derivative 1. Anybody else is 0, right? So then again, you're going to write it down here. It's going to be the derivative of r hat with respect to y hat 1 times 1, which is not needed anymore, plus derivative of r hat with respect to y hat 2, right? Nobody else showing up, right? What do you think about the gradient of r hat with respect to y3? 0. y4? y5? y6? Okay, great. You're seeing it. y7? It's not 0. Great. So it's going to be the derivative of r hat with respect to, let's look at it again here. Derivative of y hat with respect to y hat 3, right? Yeah. So exactly. So perfect. You're all seeing it. So you can start writing down all of those chain rules, and you're going to see it like this, okay? But we would not be happy if it's always like this, because it doesn't show any, systematic form, right? Interesting thing is that you can interpret this one easily as a kind of convolution, right? For max pooling, you don't see it immediately. For mean pooling, you're going to see it immediately, okay? But now let's just first visualize the whole story to get you prepared for the next one. So what I can do, I can think that this guy, this map here, this is the map which I want to fill it with the gradients of r hat with respect to whole y, right? I can think that everything here is 0 first, okay? Then I get this window, and I look at the index here. What is the index? 2, right? When index is 2, I'm going to keep this value 1. Anybody else, so index 2 is going to be 1. Anybody else is 0, okay? Everybody's clear? Now, I get this 0, 1 filter. I multiply it into this one, and then I copy everything there, okay? Now, everything was 0 here, so everything going to remain 0. Only this guy going to have this first term, this term showing up. Okay, I did a mistake here, so I should have had here first y hat 2, okay? So I just swapped the terms, sorry. Okay, but it doesn't make the final result wrong, okay? Now, the next thing that I'm going to do, I'm going to go for the next index. The next index is 1, right? So I'm going to make my filter here 1, everywhere else 0. I multiply it with this gradient at the output. I put it here, okay? Now, I already had the gradient with respect to y hat 2. Now I'm going to add gradient with respect to y hat 1, right? So each time you just make your filter with the index that you have, you multiply it at your output gradient, and you add it up exactly the place that your map is at the input, right? And you keep on doing till you fill the whole input map. Did you get what I did here? So this is a sort of convolution. But you might say, okay, it doesn't look like the classical convolution we did. Well, this is a kind of convolution. I could make it more processed, and then I show you that this is a convolution with a sort of varying filter. But I don't need to do that, because for mean pooling, you're going to see immediately. But everybody got the idea how I use chain rule, right? Right? Okay. Now, let's go for the mean pooling idea. So the moral of the story here is that when we do max pooling, now if we want to just move backward, we need to look at that gradient at the output, and we do some sort of convolution operation on that to get into the gradient of the input. Okay? But that idea is going to be much intuitive when we get into the mean pooling. Okay? So you remember I told how mean pooling was working, right? What is y hat 1 here? What is the value of y hat 1? Is the average of them. So it's going to be y1 plus y2 plus y4 plus y5 divided by 4, right? Again, y hat 2 is average of these guys, and so on, right? Correct? So I have done this forward pass before, right? And now what happened is that I somehow got into the gradient with respect to this guy. So I have the gradient with respect to this y hat map here. And what I want to do, I want to get from that gradient into the gradient of r hat with respect to this blue map. Okay? So let's do again the chain rule. So for instance, if I do the first chain rule, okay, let's look at it here. Okay, that is easier. I want to just find the gradient of r hat, derivative of r hat with respect to y1. So what should I do? I'm going to keep doing the chain rule. R hat with respect to y hat 1, y hat 1 with respect to y1. R hat with respect to y hat 2, y hat 2 with respect to y1, and so on. Okay? So if I do that, can you tell me what would be the partial derivative of r hat with respect to y1? What it would be? y1 shows up where? Let's look at it here. y1 is here. So y hat 1 is a function of y1, right? Yes? What about y hat 2? Is it a function of y1? No. Y hat 3, is it a function of y1? Y hat 4? No. So the only guy who is going to have a term in this chain rule is the derivative of y hat 1 with respect to y1, right? Y hat 2 with respect to y1 is going to be 0. Everybody else is 0, right? So this is the only guy which is going to show up, correct? So what is that derivative? What is it? 1/4. You see it, right? Because what is y hat 1? Let me write it here. Okay, I have. What is y hat 1? It's y1 plus y2 plus y4 plus y5, right? Divided by 4, correct? What is the partial derivative of y hat 1 with respect to y1? 1/4, right? Everybody else is constant, so it's going to be 1/4. So I can simply say that the gradient, the partial derivative of r hat with respect to y1 is gradient of r hat with respect to y hat 1. This is the only guy who contains y1. And that other partial derivative is 1 over 4, right? Correct? So if you do chain rule, then this is going to be 1 by 4, right? Now, let's do it together once again for y2. And you tell me, without doing any more chain rule, you just tell me what's going to be the partial derivative of r hat with respect to y2. Just tell me. Which y hats are going to show up? 1 and 2, because y hat 1 has y2, y hat 2 has y2, but none of the others have, right? And what is the terms that so I should have partial derivative of r hat with respect to y hat 1 and partial derivative of r hat with respect to y hat 2. And is there anything involved here? 1/4 here and 1/4 here, right? So now, which term has the most, or which partial derivative with respect to y? Which one has the most terms? Great, you see it. Perfect. So y5 is showing everywhere, right? So y5, so let's write that one down as well, because that's going to help us later. So partial derivative of r hat with respect to y5 is going to be 1 by 4, sum of all of them, right? Sum of all of those r hat partial derivatives with respect to y hat I, right? This is going to happen everywhere, right? And this is going to be there. So if you keep on writing down all of those chain rules, this is going to be for y5, and then again they're going to shrink, right? The others are less involved, correct? Now, again, what I could do, I could do the same thing as before. So I could say I have one filter, everybody here is 1, 4, 1, 4, 1, 4, and then I get this one, multiply it to this guy, copy it here, and then again I go for the next window, I get this one, multiply it to it, and copy it here. If there is anything inside, I'm going to add them up, and I keep on going like this, right? But there is a much easier visualization of that, okay? So let's look at that much easier visualization. You're going to see, I mean, you wouldn't get surprised after a while, but first time you might get a bit surprised. So let's look at this. Let me do some zero padding here, okay? So I got my gradient here, and I do zero padding all around it, okay? This is the output gradient, okay? And I get this filter, which is 1 by 4, 1 by 4, 1 by 4, 1 by 4, right? Everybody there is 1 by 4. This is exactly the filter which I used when I was doing mean pooling, right? Everybody's clear? Now, if I get this guy and do the convolution, what's going to happen? So I get this filter, I convolve it with this zero pad map at the output. What's going to be the first term? What is the first term when I do the convolution? 1, 4 by times? What is it? Everybody can look at, just look at it, just tell me what is it. So if I do the convolution, what I'm doing, I have this output gradient map, right? I put some zero around it, so I make it larger, and then I get this guy, and then I multiply it to this one, sum them up, write it down here, okay? So it's basically convolution. I'm getting this filter, I'm convolving it with this output, and then I'm writing it there, right? And if I do that, what would be this first term that I compute? This 1/4 is going to get multiplied by 0, 0, 0, and then here is gradient of r hat with respect to y hat, 1 times 1/4 multiplied summed up with all of those zeros. So this is going to be, this one is going to be 1/4 times gradient of r hat with respect to y hat 1, right? Correct? Okay, look at the board. It's the same thing we computed before, right? What if I go for the next guy? Do the convolution. The two top ones are 0, right? The two down ones are non-zero, so they're going to get multiplied with 1/4, 1/4. Then you add up these two guys. Look at the board. This is the gradient of r hat with respect to y2, right? So let me keep on going doing the convolution. If I get here when I'm computing the gradient with respect to y5, what's going to be the term after convolution? 1/4 multiplied by everybody added up, right? Everybody sees that? Right? So what can I conclude now? If I want to compute the gradient with respect to input when I'm doing mean pooling, what should I do? I get the gradient with respect to output, and then I convolve it with the same filter, right? So you can simply see that this guy here, what I'm doing, I'm basically doing convolution with the same filter on the output gradient, right? But what I need the input to be of size 3 by 3. Just to make it happening, I just do zero padding, right? So I do zero padding, such that I could get the same size as the input. So moral of the story here is that when you are just backpropagating through pooling layer, especially if it's mean pooling, you essentially are doing convolution, okay? So you really don't need to write down any complicated code. If you know how to write down convolution, you get the same filter, you get your output gradient, convolve it, you get your input gradient. Questions? Everybody's clear? No question?
And I hope we're going to do an example of this after, right?
We're going to do some examples, right? But I'm going to get into the convolution first. Yeah? Okay? So, moral of the story, backpropagation through pooling is a convolutional form, right? But what if it's a real convolution? It's not a max pooling. What do you guess if I want to backpropagate over a convolutional layer? Just guess. I don't want to see. Zero padding convolution again. Yeah, it's going to be convolution. And it's not a surprising result because convolution, I told you, is a linear operation, right? So when you compute the derivative of a linear operation, it's going to be the coefficient, right? So the backward operation and forward operation for any linear operation is always the same, right? You only play around with those weights, right? You resort them. And this is the same thing. Forward is linear, backward should be linear. It cannot be nonlinear, right? Slope of a line is always fixed. It's not changing, right? So we're going to see it right now, so hopefully. But if we are doing convolution, then essentially we have one activation at the output, and before that we had a convolution. The activation is easy peasy for you, right? So when you have activation, you just simply need to know the entry-wise derivative, and then you multiply everything. So that is quite obvious. If you have derivative with respect to y, then the derivative with respect to z, the partial derivative with respect to z, is going to be this product. Yeah? So you get your gradient, and you just multiply every single entry with the corresponding derivative of the activation function at that point, right? Same thing as we did in the fully connected networks, right? So that is easy. We're going to get into the output of the convolution operation, but then the question is that how we can go backward on this convolution layer, okay? And then again, we can do exactly the same thing we did with mean pooling. So let's look at it again. So what I assume now I have weights W1, W2, W3, W4, okay? I have these 4 different weights. And now what I'm going to do, I'm going to get this guy, I filter this input, and then I write down the output map. Meaning that Z1 is basically these weights multiplied with these inputs added up. Z2 is depending on these guys, Z3 depending on these guys, Z4 depending on these guys. And now what I assume that I have the gradient with respect to Z, the output of the convolution. I want to know what is the derivative or gradient with respect to X, which is the input of the convolution. Everybody's clear? Questions? Okay, so if you got clear, then can you tell me how I can do it? Again, look at this one. If I want to do chain rule. So if I want to, for example, compute the partial derivative of r hat with respect to x1, what should I do? partial derivative of r hat with respect to z1, and then z1 with respect to x1. Partial derivative of r hat with respect to z2 with respect to x1, and so on, right? So you're going to do this chain rule, right? Now, the only thing that we should pay attention here is that where is x1 showing up? Where is it showing up? It's showing up in z1, but not in z2, z3, and z4, right? So what would be this partial derivative? Partial derivative of r hat with respect to x1? Perfect. W1, which is this partial derivative, times partial derivative of r hat with respect to z1, right? So you can keep on doing this with the chain rule as before. So you're going to compute the partial derivative with respect to x1. It's going to be w1 with times this derivative. For x2, x2 is showing up in two different values of z. So two different terms you're going to have in this chain rule. And you can keep on going. Which term or which partial derivative is going to have the most terms? x5, exactly. x5 is everywhere, right? So x5 is everywhere. And if you keep on doing it, you're going to see that x5 is having the most terms. Okay? So you can keep on going like this, as I told you, exactly like what we did with mean pooling. And then you can, again, try to visualize it in this form. So you would say, OK, I have this filter getting multiplied here, or I did there. And then I keep on going like this. But we can, again, do it exactly the same way we did it with mean pooling. OK? And how it's going to happen? It's going to be, again, one filter being convolved with this output gradient, and then you write it down there. OK? So it's exactly the same thing. But there is one tiny change here. What is that? What's going to be that filter there? It's not it exactly. Look at it. What do we have at the partial derivative of r hat with respect to x1? W1, right? So if I am doing the convolution, where should be W1 in this filter? Here, right? So if you play around with it, you're going to see that you're going to have your filter, the same filter as before, just reversed. Left to right, top to down. OK? So your filter is reversed only, but you are still doing a convolution, right? So it is somehow like the transpose we had when we were doing the fully connected layer, right? So we go with transpose, then when we want, with the matrix itself, but then we transpose it when we want to go backward, right? So it's somehow that operation. Okay? You just resort your filter. Moral of the story here, so you can go ahead and do all of these computations. You're going to see that happens. And the moral of the story, the most important thing that I wanted to just let you know for today was this idea that once you are going backward in a convolutional layer, you essentially do again a convolution, right? The only difference is that you resort your filter. And in this example, when you are doing 2D to 2D, like one map to one map convolution, then the backward filter is going to be the reversed one, which is reversed left to right, top to down. Okay? Everybody's clear? Right? So, moral of the story, your gradient with respect to input is going to be the convolution of your gradient with respect to output with the reversed filter, right? And this reversed filter, we're going to play around with it. For the three-dimensional case, you again have the same thing, only the reversion is a bit different, okay? How you resort those filters is a bit different, right? By the end of the day, you always, when you do convolution forward, you're doing convolution backward. And this is the whole good thing about the computation part of CNN. Because you are going again